You remember?
All right. Okay, so chapter 10 homework is what we're looking at, right?
Mm-hmm.
So let's go to the main page here. Chapter 10 homework. All right, which number we want to look at?
Okay, let me go over to it as well. And you can full zoom. Okay. Let's start with 4.
Okay. So we have a 3-kilogram cat near the edge of this 6.5 meter diameter merry-go-round. Man pushes and accelerates the merry-go-round at this uniform rate of 30.35 radians per second squared. So that's an angular acceleration. And the cat hangs on, but can only hold on with 160 newtons of force and eventually flies off. Okay, so let's see here. Do you like my quarantine hairdo?
Take a look. Have you not been able to go to the barber? Oh, it looks good.
It's sticking out in all kinds of places. It's because I showered last night and slept on it.
That's the biggest mistake. I agree.
Yeah. I spent almost the whole day yesterday sanding drywall in my house, so I was covered in dust. I looked like Santa Claus. So I had to shower last night.
So you're gonna be one of the people that's reinventing their whole house and stuff?
I was already doing that. I'm spending more time doing it now that I'm at home more. So
Oh.
I was already in the middle of it. All right, so here's our merry-go-round. Woo! Look at that, fancy. And we have a force pushing on one side of it from the man pushing here, right? And then we have our cat. See, we'll make our cat a little diamond. There's our cat. Now the cat, that's right here. This is the force that's pushing here, the push force, right? And then up here we have a force from the cat that's holding the cat in. So this one is the centripetal force that holds the cat onto this thing, right? Come on already. How come I can't move this thing? Oh well. So the centripetal force holds the cat onto the merry-go-round. So that force pulls the cat inward, right?
Yes.
Centripetal forces always act towards the center of the rotational motion. So that's the force of the cat's claws, in other words. We have the pushing force on the outside, and we have the centripetal force holding the cat on the inside. Now, what are the things that they've given us? Some of the things that they've given us are, they've told us that the centripetal force is equal to some number. They've told us that, right?
Mm-hmm.
We'll say it's whatever it is. I think 160 was or something like that. And have they told us the pushing force that the man pushes with?
Hang on, I think we have different numbers. I got the force from the cat is 210.
Okay, well, it doesn't really matter what it is. It's just some number, right?
Yeah.
They don't tell us the pushing force. That's a question mark there. So that one we can just actually get rid of. They do tell us the pushing acceleration, though. They tell us that the acceleration, which is alpha, right, equals, in mine, it's 0.35 radians per second, right? Dang it, why can't I make this work right? So they've told us that the centripetal acceleration is 0.35 meters per second squared, right? Let's see, what else have they told us? They've told us the diameter of the merry-go-round. So the diameter of the merry-go-round is whatever it is.
I have 6.5 meters.
Mine is, I don't know what it is. Yeah, 6.5. So diameter equals 6.5 meters. And they also tell us the cat's 3 kilograms and near the edge, right?
Yeah, where'd you get you have an alpha 35 meters per second squared?
0.35, yeah. Oh, no, sorry, not meters per second. It's radians per second.
Oh, okay. Because I just have 1 radian per second, so I wasn't sure.
That's fine. I don't know if I can erase that or not. Oh, there we go. Now I'm actually selected it. That's what I want. So this is radians per second squared. Sorry. All right. Diameter 6.5. Okay. That's everything, right?
Yes.
Yeah. So the things that they want to know, the first thing they want to know is the tangential velocity of when the cat flies off. So the centripetal force, one of the equations that we have for centripetal force is that centripetal force is equal to v squared over r. Tangential velocity squared over r, right?
Yes.
And so at the maximum tangential velocity will get the maximum centripetal force, right? So this is the equation you're going to use for the first part. Is that the one you used?
Yeah, I got velocity and I got angular velocity.
So you got the angular velocity by doing what? Because did you use a what am I thinking? My brain just turned off. Did you use one of the kinematic equations to get the angular velocity?
Yeah, I had centripetal acceleration and I had that equal to tangent velocity squared over r, and I just filled that in.
Good.
So what we're doing now.
You used not a okay, I see what you did. You just converted. That's fine.
Mm-hmm.
So what you did for omega, you said that omega equals the velocity tangential over r, right? Over the diameter. This says the diameter here, so you divided the diameter by 2, right?
Mm-hmm.
So divide by diameter, divide by 2, like that.
Mm-hmm.
All right, so that's your second part. And then how long did it take to do this? So how long it took is going to be a kinematic equation, because now that you know omega, you know your initial angular velocity, which is 0, you know your final angular velocity, which is this one, and you know the angular acceleration, right? Because that's the alpha right here. Then there is an equation that will give it to you, and it looks like this. Looks like omega final equals omega initial, which is just 0, so we'll leave it off, right? Plus alpha times time. So you just divide omega divide this omega that you just calculated by alpha, and you'll get the time.
Omega's the W, right?
Yes.
Sorry.
Yes, that's correct.
Right, alpha, and you get time?
Yep.
Okay, that's interesting.
And then how far did it go? How far did it rotate? Well, there's another one. There's another kinematic equation that says omega final equals, no, it says theta final. There we go. Equals theta initial, which is 0. So we won't put it in, equals omega times time. No, that's for constant omega. Sorry, we don't have constant omega. We want to do the final theta equals initial theta, which is 0, time plus initial omega times time. The initial omega is 0, so those first two terms go away, plus 1/2 alpha times time squared, 1/2 alpha t squared. So you're going to get alpha times time squared divided by 2. And then you solve this one for time.
Wait, didn't we just solve for time?
No, you solved this one for theta, sorry. Yeah, you solved this one for theta, not for time.
So theta actually equals omega over alpha.
No, theta actually equals alpha times time squared over 2. Right here.
Can you repeat that one part?
So if we go back to the book really quick, let me show you this in the book because it's a little confusing the way I'm writing it, I think. Let me see. Okay, table of contents.
Yeah, because are we trying to solve for time first or theta?
We already did time. Time we already got, right?
Time was the omega over alpha.
Yeah. So we got the time from this equation right here. Omega equals omega naught plus alpha t. So we divided omega by alpha to get t, right? For the theta, we can use this equation here with our time that we just calculated, which is the one I just did. So theta is going to equal omega naught. Well, omega naught is 0, so that goes away. So theta equals 1/2 alpha t squared. So essentially, you're just going to plug in 1/2 in your alpha and your time squared, and you're going to get theta. Or you can use this equation to solve for theta. Either way, it works. This one's probably easier. So this table right here becomes extremely important.
Yeah, I might have to mark that one down then.
Yeah, that's a good one to mark. It's a good one to just like print off or copy down or something too for this section. So what's the next part of this problem? How many rotations? So you take however much angle you have, however much theta you have in radians, how many radians are there per rotation?
2 pi.
2 pi. So you take that previous answer and divide by 2 pi, and you will get the number of rotations you've gone through.
Do I not have to multiply by 60 or anything?
Multiply by 60. Nope.
So I just take, that's a little confusing because that's how I found the others. So I would take theta and divide it by 2 pi.
Yeah, because when you were before, what you were doing is you were converting between rotations and theta, right? You were doing rotations per minute, and that's why you did the 60 is because the per minute thing has a 60 involved.
Oh, okay.
Right? This is just how many rotations total did it go through, right? It's not talking about how many rotations per minute. By the way, we have officially canceled everything for our trip to Washington, D.C.
Oh, really?
Yes, so you will soon be getting and that's mostly because everything that we were going to see is now canceled through May.
Oh,
and so we even if we decided to go, we couldn't go see anything.
So it's like really
everything is closed.
Nice.
So what we're going to do is we're going to refund everybody their $150. You should be getting a check in the mail in the next month at the latest, I would imagine. And then also, I'm going to try to see if we can use the money that we spent on those tickets for next year, because Southwest is holding the money in reserve for future flights for us. If that doesn't work out, you might actually get a $200 voucher for, actually be a $220 voucher, or $230 voucher for a Southwest ticket to use any way you want to.
Hey.
It's possible, because I'm not sure if Southwest will let me use those because they have your name on them.
Oh, okay.
If they won't let me use them for STEM Club next year, then you might get a bonus of a free voucher for using on Southwest.
That'd be interesting.
Yeah, we'll see how it works out, but at present, it's still in the air. But the $150 will certainly come back to you, and we will send those. We'll hopefully try to cut those checks next week and get them to you as soon as possible.
That sounds good. Thank you for letting me know about that.
One of the reasons that I mentioned this is that you need to, and I'll need your home address just email me your home address at some point so that I can send it to your house.
Yeah, sounds good because I'm not in Nebraska currently.
All right, so then the last two here, centripetal acceleration. I think I lied to you before, so I have to unlie to you. Hold on just a second, let me check.
What?
Yes, I lied to you right here. This is not true. Force centripetal here. Come on, how do I get into that again? There we go. This is actually equal to mv squared. The centripetal force is equal to mass times acceleration. V squared over r is actually equal to the centripetal acceleration. So if you do another equation here for the centripetal acceleration, a centripetal acceleration actually equals v squared over v squared over the radius. So what you calculated in part, what you used to calculate your tangential velocity would actually be your centripetal force. So you have centripetal force is 160 newtons. And if you wanted to calculate your tangential velocity from that, you would use this equation. Centripetal force equals mass times velocity, tangential velocity squared divided by r, because the centripetal acceleration actually equals v squared over r. So make sure you make that change when you calculate the tangential velocity. Use the mass in there as well, and then your centripetal acceleration is part of that equation, v squared over r. And then can you guess how to figure out the tangential acceleration from what you know in this problem? Did you already do that?
The tangential acceleration?
Yeah.
Oh, that's what I was writing down. Because I figured out the centripetal acceleration. Yeah, that was no problem. It was the tangential that I got wrong.
So tangential acceleration, what did you do to calculate that?
To get tangential, I did radius multiplied by alpha. Is that what I wrote?
Yeah, that should be correct. So it should be your radius, which is half your diameter, of course, multiplied by alpha. And what did you get? What was your answer for that?
Well, it was wrong, so I just deleted it, but it should be 3.25.
So 3.25 times, and what's your alpha? Your alpha is 1.
Yeah.
So it should be 3.25. That should be correct. I don't know why it marked it wrong, but I'll check that later.
Let me see. Okay, yeah, it seems like it accepted all the answers. So that makes a lot more sense. I've been having trouble with those. Like if I keep going on to like 5, 6, and 7, I'm having trouble with just finding like acceleration and like angular acceleration. I don't know how.
Well, let's take a look here again. Okay, so the downward acceleration of the block is going to be like the linear acceleration of the string, right? Let's see here. So the string is accelerating along the edge of the block at the same acceleration as the string is accelerating downward. In other words, your tangential acceleration is equal to your linear acceleration. So what we got to do is we got to figure out what it is that there's going to be a relationship between how fast this thing is rotating and how fast this thing is falling, right? Mm-hmm. The problem is that this is a fairly complex problem because they've told you that the cylinder, the pulley, has mass. Yeah. And so this is actually going to be a problem that includes the moment of inertia of this cylinder. So this is much more complex than it seems from the start. So let's go ahead and
Mhm.
Whiteboard again here. And let's clear all that. So here's our, I'm going to use the circle. I'm going to draw nice things from now on. There we go.
Looks good.
Might as well if I can, right?
Mhm.
So this is the pulley, and it's going to have a force on it this way. This force that is this way is going to be the weight of the block, right? So we have the force from the weight of the block pulling down on it this way, right?
Mhm.
This thing has a radius associated with it, right? Radius R, whatever that is. And it also has a mass associated with it. So we'll give it a mass, M. And that's pretty much all they give us, I think, right? They give us the mass, they give us the radius,
And then the other mass.
and the other mass. So this mass here actually has, hold on.
Yeah, we said it's 0.25 kilograms for that small mass.
I want to change that mass. Let's change this one, I guess. Ah! How come I can't change this equation?
Is something wrong with it?
Got it. This is going to be the mass of the block.
Okay.
It's going to be the mass of the wheel. Okay, so two different masses right there. So this is not just a kinematics problem. This is definitely a problem that involves forces and torques and rotational things and stuff like this. So we have to consider all those things. So how do we consider this? Well, we're going to consider the force, this force downward causing a torque on this thing, which is going to cause this to angularly accelerate, right? So the torque involved is going to equal, so the torque, did I spell out right? I did. Sure.
Yeah.
So the torque equals the force times the distance times the angle between them, right? And the angle between them is 90 right here. So the sign of the angle is just 1, so we can just equal the force times the distance. So it's going to be the weight times the R, so it's going to be mb times G. Times R, just like that. That's our torque. Now the torque is going to be involved in an equation for Newton's second law, which says that torque equals not mass times acceleration, but moment of inertia times angular acceleration, alpha, right? Because that's the new equation when we're talking about rotation, right? What is the I then? We need to figure out the I. Well, the I for a disk, where's my I? There we go, I. The I for a disk, if we go back to our book and we look at the different moments of inertia, where are the moments of inertia?
That's on 10.3.
10.3, there we go, yeah.
That's searching for it too.
Moments of inertia we need for a disk, it's mr squared over 2, just like normal, so that's great. So it's the mass of the disk times the radius of the disk squared over 2 divided by 2. So that's our I. Great. Now, can we figure out alpha from everything that we have here? We know the mass of the disk, we know the radius, so we know I. We know the torque because we know the mass of the block, and we know G and we know R. So we know everything we need to know. All we need to do now is solve this equation, solve all these equations to get out alpha, right?
Is the mass of the disk the pulley or the block?
The mass of this little m here is the mass of the disk, the pulley.
Oh, that makes sense.
This MB is the mass of the block.
Okay, just double checking.
So what we're going to do is we're going to plug the torque into this equation, and we're going to plug the I into this equation and solve for alpha. So the torque is MBGR. So MB times G times R on one side. That's the torque right here. And then the I is mr squared over 2, m times r squared over 2. Put that in parentheses. And then we multiply that by alpha. And then we solve for alpha. So we divide both sides by mr squared over 2, and we get alpha. Does that make sense?
Yes. Multiplying that one by alpha. We were just trying to get alpha. That's what's going on.
Yeah, so in the problem, the first thing they asked for is alpha, I believe. Oh, no, the second thing they asked for is alpha. So we're actually solving for alpha before we solve for the acceleration of the block, which is fine. Because the downward acceleration of the block is related to alpha by r, isn't it?
I think so.
Because the string is traveling around the outside of the disk, the acceleration of the string downward, which is the same as the acceleration of the block downward, is going to be equal to a, which equals r times alpha. So that's the last equation we draw in here. A tangential equals alpha times r. Tangential acceleration equals angular acceleration times radius. And then the last three, or the last two, are questions that you use kinematic equations to solve for. They want to know how much time it takes. Well, there's a kinematic equation that uses alpha and initial omega, and let's see, what else do they use? And what do they ask there? Oh, and distance, and then you can use time to get it. So one of the kinematic equations, it's the one that has omega squared in it. Omega squared equals omega initial squared. So
Wait, I'm confused. How do we find the time?
So now, once we're done with all this stuff, we know alpha, right?
Yes, I got 294.
So then in the next part, they tell us the distance that it travels, right?
Oh yeah,
Distance is
1.14.
1.04 meters, right? And we know how fast it's accelerating. We know a. So you can use a linear kinematic equation to calculate t if you know distance and acceleration. So go back to the linear kinematic equations and find the equation that will give you distance, that will give you time if you know distance and acceleration. Does that make sense?
Time would equal.
If I'm remembering correctly, that's going to be, let's see, kinematics, here we go. So if we know distance and acceleration, so it's going to be the third equation down in the table 10.2 on the translational side. So
Just distance divided by, or acceleration divided by distance, right?
It will actually be not quite like that.
No?
Let's see, here it is. It's this equation here.
Oh,
You're going to take your distance, you're going to divide it by acceleration, you're going to multiply it by 2, and then you're going to take the square root.
Let me see your screen 1 second.
So it's this equation here.
We
know the initial velocity is 0, right? We know the final distance because they tell us the 1.04 meters that it drops, or whatever it is for your problem. And we know the acceleration because we just calculated it.
There's 2 t's. Oh, because of the 0. So that'd be 0.
The first term is 0 with the t. First term goes away.
Makes a little bit more sense. Yeah, so then I got t squared equals 0.026. That seems like a really small number.
How much is it?
0.16.
No, that's not that small. That's not that small.
Okay. Oh, you're right. Okay.
Things fall very quickly,
They do tend to do that.
which is kind of funny because when you think about sports, for example, and you think people in basketball, they talk about hang time, right? That guy has
Yeah.
a ton of hang time. Well, in reality, the maximum hang time any basketball player has ever had in the NBA is less than 2 seconds.
Oh, that's weird.
Yeah,
Didn't
and
know.
it's more like 1.2 seconds, 1.1 seconds is about the maximum hang time. The maximum hang time for a volleyball player, a little bit higher, maybe 1.5 seconds at the absolute highest. For a high jumper, 1.6 seconds, maybe
Jeez.
1.7, not much higher.
Well,
You
if you
know,
think
you
about that
can't
at the same
once
time.
once you're jumping at once your hang time is at about 1.6 seconds, you're clearing 2 meters. You're clearing 6 feet.
Oh my gosh.
So that's really high, and only high
Ew.
jumpers can really get that high. So, and one of the reasons they get that high is because they land on their back. They
Oh,
don't land on their feet.
that is true. High jump kicked my butt in high school, so
What's that?
I said high jump kicked my butt in high school, so I
High
feel that.
jump is high jump is challenging. I actually
Mm.
played volleyball with two high jumpers from the university I was at, BYU, and man, they could jump like crazy. They weren't great at volleyball, but they could really get up there.
That's what counts.
Neither of them were tall. It was crazy. They just jumped like crazy. So,
Mm.
all right. So number 6, you said you also want to talk about, or do you
Wait,
have more questions on number 5?
well, number 5, how many revolutions did they deploy make? You
So
don't divide it by 2 pi anymore, do you?
yeah, it's the same thing.
Really?
So once you've figured out how much angle it's gone through, you just divide that by 2 pi, and it gives you the number of revolutions again.
Okay, I must have been, because I think when I was using that example with the time using by 60 first, it threw
Yeah.
me off.
Yeah, and that's always the case when you go from RPM to just revolutions. RPM has per minute in it, so you have to account for that time, changing it from minutes to seconds. And since there's 60 seconds in a minute, then you have a 60 involved. But we're not talking about revolutions per minute, we're just talking about revolutions.
Okay, and then if the radius of the balloon was increased, it acceleration would increase too, right?
Yeah. So I've discovered a really great thing about this whole quarantine situation. I have all kinds of time to clean my office and my classroom.
Really?
I'm gonna actually look like somebody who's got it all together when everybody comes back.
Yeah,
That's
I
cool.
guess it says that my downward acceleration of the block, my angular acceleration of the pulley, and my time is still wrong.
Oh, well, that's not good. All right, let me take a look here. Let me go back to, okay. Since I'm recording this, I don't want to show your grades to everybody,
Hmm.
since that's not kosher nor legal. You're not seeing my, you're just seeing my face now, right?
Yeah.
Sorry about that. All right, number 5, 6, no, 5, 4, 5.
We're on 5.
Uh, okay, you've got everything right except there's a power. Well, the time's not right. That we're off by a power of 10 for some reason.
Oh, what? For which one?
For the first two, my
Okay.
answer is 88.2. The answer in the book shows 8.8. 1.1.
Yeah. Well, does it say my radius is 0.03 or 0.3? Because that's what I have.
Your radius, it says it's 0.3.
Yeah.
Mass is 0.25 kilograms. 1.1 kilogram. Um, hold on just a minute while I work the numbers through really quick. Okay. Mass of your block is 1.1.
Yes.
Mass of the cylinder is 0.25.
Yes.
Okay, so I get a number more like theirs. I'm not sure what you did differently, but when I multiply in the formula that I end up with 2 times 1.1 kilogram.
Wait. Well, because if we're looking at, let me see the first part that got messed up. Okay, so the 88.2, I got that from radius times alpha. And I got alpha from the mass times gravity, like the block mass times gravity times radius is equal to um, the inertia and then times alpha. Yeah.
Hold on a second. No, that's not right either. Um, yeah, I actually get the same answer you do.
Mm-hmm.
Let me look at the code here. Squared. Mass of the pulley. Okay, let's see. Their answer is okay. They're saying acceleration equals mg to Why are they saying that? Ooh, I have no idea where they got this formula from. This is a weird formula. Looks nothing like our formula. And I can't think of any reason why our formula would not be correct. But I can't think of a single reason that theirs would be. I can't figure out where they got that from.
Huh.
It's nothing even, they're obviously approaching this problem very differently when they solved that, created that formula, and I don't know where it's coming from.
We did solve for alpha first.
That shouldn't matter at all. That shouldn't matter in the least bit at all, but I don't know. Let me see here. Um, all right, let's go back and check this again. So it gives you the correct, you get the correct number of rotations though,
Yeah.
revolutions.
Yeah.
So theirs has to be wrong because you used your previous numbers to get the total number of rotations, right?
Well, here's the thing too. I had the correct number of radians before I entered this problem. So they said my previous was wrong too. I think that was like the only thing I had right.
I think
Oh, I submitted again. Oops. And then I had time wrong too, which is confusing.
there's also the third question on the 4 questions below, the third multiple choice question is also incorrect.
Which one? If the radius of the pulley were increased, the acceleration would not change. I fixed that.
So, but that's actually not true.
Really?
No,
I
it's
said
the
it would
radius,
increase.
because according to our formula, alpha, let's see.
What's the true answer to that then? I thought if the radius
Well,
increased.
I'm not sure. Hold on just a second. Actually, it's true that A will not increase, alpha will.
Oh, okay.
But A
Alpha
will.
will increase, A
Yeah,
will not.
yeah, A will not increase. That is true, according to our formula. But if our formula is correct, then theirs can't be. My
Oh,
guess is that we've done it right and they haven't, but I'm just going to give you the points. And I'll have to go, I'm going to go in and change the code later. I have to make a note for myself, but I'll just give you those points.
and then since we're rearing the end of our session, I swear I got 10 and 11 right. Like, I don't know how other way I could have solved
Let's
it.
check here. We're on homework 10, right?
Yeah. And then if you can email me, like, I don't know how quickly we're done. How to even start number 8, I got confused with.
Let's see, 2 times. Okay, one thing that you'll have to realize is that there's definitely going to be some omegas involved in this answer. You have only, I mean, some thetas, not just omegas. You have omegas, but you don't have thetas, and you can't write it as W either. You have to write it as omega.
Yeah, it would. I couldn't find it, but let me see.
So what you do is, let me see if I can show you this really quick. Let's go to here, chapter 10, number 10.
Yeah, 10 and 11 are both equations.
So when you click in this box, go over to this little arrow.
Yeah.
And it gives you some tools to work with. Let's
Yeah.
see if I can find them here.
Yeah, I was on all those.
Okay, so you can use that. So what you do is you go here and put omega. In fact, you can just put an underscore if you want. If you just do an underscore 0 like that, and then let it preview for us. See, it won't let me preview. Does yours have a little preview button?
No.
Oh. Does it show you anything while you're typing?
No.
Okay.
It used to. This module has not so far.
Okay, so I need to fix that. Then you can also use this one here that puts it under like that, right?
Yeah, that's the one I usually use.
On here, it shows you the preview.
Okay.
So then it just shows you how to do it. But you're going to have some thetas in there as well. So go back and think about the equations that you used and see if there's a different one that will work better.
Yeah.
And for this one, the same thing. There's something that you're missing from them that you didn't account for, is all.
Yeah.
So
11, I'm super confused with too. Okay.
So in these problems, they're saying that it has a rotational kinetic energy K and a rotational inertia of I. So what you do with these kinds of problems is you go to, what you want to do is write down the equation for kinetic energy, for rotational kinetic energy.
I have that.
Write down the equation for the rotational inertia, I, right?
Yeah. Yep.
And in one of those things, you're going to have omega. And and then you're going to solve. Well, actually, no, you don't even have to just write down the equation for rotational kinetic energy, actually.
Yeah.
And then solve it for omega. And that's all you're going to do here. So
I swear that's what I did, because it's K equals 1/2 times inertia times W or omega squared.
right.
And so after I did all that, I got omega equals the square root because of the square.
Yeah.
K over 1/2 inertia.
Are you using capital K?
That's a good question. I was not.
Yeah, it'll require you to use a capital K. Just resubmit and send me an email to remind me to check that, and then I'll give you the full credit for it.
Let's see.
Actually, I can check.
Yeah. Yeah, it's good now. It's okay. I got 1 out of 1 point anyway.
Okay. All right. So go ahead and keep working on this. If you have more questions, you know, message me or whatever. When is this due? I don't remember.
In about 11 hours.
Okay. Do you want me to give you more time on it so you can ask more questions on Monday, or do you want to just try to figure it out? Because it doesn't matter either way.
Let's do it just in case, but I plan on getting it done tonight.
Okay.
I definitely do. I'll probably need an email for question 8 because that's the only one I couldn't even attempt. I didn't know where to start with that one.
Okay. Sounds fine. Yeah. In fact, if you just send me a message asking about question 8, and I can actually send you a video. We can do it right now if you want. I've got time right now if you have time.
I'm at a work environment right now too.
That's okay. No worries. Just send me an email. Send me a message through my open math, and then I'll send you back a little tutorial on it.
Okay. Do you want me to say anything or just send the?
Yeah, just say I need help with this one, or if you have any details about things you didn't understand, include that too. All right.
Okay. Thank you so much.
We'll start chapter 11 on Monday.
Great. Thank you again. I'll see you on Monday.
Have a good weekend.
You too.